Hello everyone, today I'm going to talk about the comparison of personalized biodegradable vascular stent and narrow stent by measuring young modulus value and observing physical features through a microscope, but in a math part. Okay, so our project is aimed to compare two different types of stent to find the transition of stent in different body conditions. The first type of stent that we use to compare is the arrow stent manufactured by Weng Wu. And the second one is the stent of our self-designed vascular stent, and both of stent are polylactic acids and have negative Poisson ratio structure. And the blood condition that we use is the high glucose in blood and regular blood pressure, and another one is the high blood pressure. And we performing simulation that mimic the blood circular system by using a water pump and pipe in conducted in this paper. I mean, we use pipe and pump to simulate this blood in circular system, and we use Bernoulli equation and Stokes law and Hagen-Poiseuille. Next, and here is our prototype design that we have designed for our stent. Next.
Okay, so as Non said that we will make a blood simulation, so we have to make a liquid that has the same viscosity as the real blood and has the same density. But the problem is that we still don't know whether we will use starch or aqueous glycerol. So as soon as we know already that what we will use, we will have to select one of them, and we will have to measure the viscosity of it by following this procedure. Next. This is a procedure that I'm talking about. We follow the mathematical model part of the paper called measure liquid viscosity by tracking falling ball automatically depending on image processing algorithm. This is the name of the paper that I use to be a reference in order to find the viscosity of the bud-like fluid. So let's talk about this part. It's the pure math part, and we have many equations right here. So let's me explain you about the variable first. Fd is drag force, mu is viscous friction. This is the thing that we want to find. And I is the radius of falling ball. V is the terminal ball velocity in liquid. And D is the ball diameter. Rho B is ball density. Rho L is liquid density. And G is the earth gravity, which is 9.8 Newton over meter square. And this is our formula we're talking about in next slide. Next. This is our slide, and this is a free body diagram of the ball when it is falling down the cylinder tube. Fd equal to 6 pi mu rv. This is the Stokes law that Non has mentioned in the first part. So Stokes law describe the drag force. So as you can see in the ball, the force that applied to the ball, which is going up, have two forces, which is buoyant force and drag force. And the force that applied the ball to go down have one force, which is a gravitational force. So when the ball goes down in the constant velocity, it means that the acceleration is zero. So in physics, this is counted to be equilibrium state. So that's why when all the forces are applied together, it will equal to net zero in the second sentences, which is Fv plus Fd plus Fg will be equal to zero. It will be passed in the vector form. And the third sentence is Fb is buoyant force is equal to density of the ball, which is 4 over 3 pi r cubed times rho of liquid times gravitational Earth gravitational value, and path Stokes law will be equal to mg and it's going down. So we'll just have to move variable, and then the final thing that we want is the viscosity, right? Which is represented by mu. Mu is equal to d square uh, times rho v minus rho L and times G over by 18V. This is the final formula. So I have to get the ball into the liquid, which is maybe a glycerol or a starch, in order to test it and find the viscosity of it. And after I already found the viscosity, I have to get the fluid into the simulation, which is going to be a next step next.
So, okay, so in order to proceed to our blood circulation simulation, it is crucial to know the blood pressure value that we are going to use in the simulation, including the systolic and diastolic pressures. So we need to use a simple calculation through these three principles. The number one is continuity equation. The second one is Bernoulli principles. And the third one is a Hagen-Poiseuille equation. So this is our illustration of our simulation of the blood circulation simulation. So we have the 3 point right here, point 1, point 2, and point 3. The pressure at the point 1 will represent the equation 1 right here, the P1 plus 1/2 of the rho V1 square plus rho GH1. And followed by the second equation, which is the same term, but change the point with a different point. So you will notice here the rho GH2 will be cancelled out. This is because the H2 or the height at the point 2 will be equal to 0, because we assume that we place the simulation on the ground, and we assume that the height at the point 2 will be equal to 0, so y will be equal to 0. So we assume that, so it's going to be the 0 for this term. So from the Bernoulli equation, we have to make the equation 1 and equation 2 equals. So we're going to be like this. And from the continuity equation, the A1 V1 will be equal to A2 V2. The A will represent the area, the cross-section area at the point 1 and point 2. So you will notice that the cross-section area of the pipe at point 1 and point 2 will be the same value. So it will cancel out. So we will get the V1 will be equal to V2. The V represent the velocity at point 1 and point 2 respectively. So we need to substitute this term into this equation. So the second term of each side will be cancelled out, and we will get the pressure at the point 2 from the Bernoulli equation. And you might be wonder why the P1 turns into the PA. The PA represent the atmospheric pressure, and you will notice that the point 1 is actually present in the air, in the atmospheric pressure. So the P1 will be automatically turned into the atmospheric pressure. So P1 will be equal to PA. So in order to find the pressure at the point 3, we're going to use the Hagen-Poiseuille law. So in the Hagen-Poiseuille law, the equation has the delta P, or the change in and the pressure in different 2 points. So in this case, we will use the P3 and P2. So it is the change of the pressure between point 3 and point 2. So P3 will be minus by P2 right here. And we will simplify this equation into the right side equation right here. The P3 will be going to equal to this term plus by the P2. The P2 is the pressure at the point 2 that we calculated in the previous slide. So we substitute that term and we will get this equation right here.
As PP already proved the equation, so in the procedure part, I will just have to use it. So I have to find the pressure at the point 3, and in order to do that, well, do you know that when we are living right now, we are living because of the heart is pumped, right? And when the heart is pumped, it will have two value of pressure. One is the systolic pressure, and the other one is diastolic pressure. And same as our simulation, we have to alternate the blood pressure between systolic pressure and diastolic pressure. So the way to do that is to cut the hole under the tube in order to alternate the pressure and using the servo, which I will talk about it later in the diastolic part. But in systolic pressure, I have to use two value pressure, right? I have to find that. So let's talk about systolic pressure first. In systolic pressure, we have to find the pressure in point 3, and in order to find that, we have to adjust the value L. As I said here, that L is the independent variable. So if we adjust L, we will adjust it until the P3 value reaches 760 part 130 millimeter mercury, and also 760 past 160 millimeter mercury. This is the value that I have to adjust L in order to find this kind of value. And when we already know what L will give us these two values, we'll just keep it. So when we connect the pipe to the pump, we will know exactly what length of pipe we will use. Next. And when I have said that I have to alternate by pressure, right, between systolic and diastolic. This one, we will have a hole and have a servo. The part when the servo covers the hole, that will be systolic pressure. But when the servo does not cover the hole, you will have partial part of the water coming out, and that will reduce the pressure, and the pressure will be remain to be diastolic pressure. That is the mechanism of our experiment. Next. So in order to find diastolic pressure, it's a little bit more complicated than systolic pressure because I have to cut the hole, right? But the independent variable will be changed from L to X, which is the size of the hole. So we just have to adjust the size of the hole until the pressure 3 reaches 760 past 90 millimeters mercury and 760 past 100 millimeters mercury. This is a value that we want. So after this experiment, we will know the size of two sizes of the hole that makes 90 and 100 millimeters mercury possible. You might have a question, why I have to pass 760? So when you go to a doctor, when you when the nurse comes to measure your pressure, you have two values, right? And for normal people, it will be 130 and 90. That pressure right there is not the absolute pressure, it's a gauge pressure. So if we want to find the absolute pressure, we have to pass the atmospheric pressure. So that's why it is 160 and it is atmospheric pressure when we pass the gauge pressure will get absolute pressure that we want. So that's why we pass 760 in the value. Next. And this is just the prototype of our experiment. This will put a stent at the location according to Lx that we found, and just put a hole in the hole, and that's really it. That's the end of the math part.